Okay, start? Okay, good morning, good afternoon, everyone. So we are working on classification on fake and real articles. I'm Justin, this is Ajia, this is Wenyi, and this is Xiaohua. So the outline of our present is that we are going to have brief introduction for the task, and then we did some training set balancing, and then I think the main point for our present is our feature extraction, and basically it's like we split that into 3 categories. For each of them, we'll have the respective person introduce the stuff, and then we'll present our result. So the task is it's the general task. So our goal is to distinguish between real articles and the fake articles, which is generated by a really strong trigram, training from a huge, a sort of big word corpus. And the approach we are going to use is trying to use the SVM classification, so with a famous tool called libSVM. So a side note for this is libSVM is from a Taiwanese professor, which is my country, so that's pretty good. So and we did some balancing because we figured out there is some different article length properties with that there are some difference in training set and development sets, and then we did feature extractions. So the goal is kind of to find a feature that is different from real and fake articles and use that to do the classification. So for the balancing,
yeah. So the reason we did the balancing is because we observed that the distributions of numbers of sentences in each article in the training set is quite different from that of the development set. And the experience told us that most machine learning algorithms need the distributions of both the training and development set to be similar or the same. So we just used a simple algorithm to balance the training set by dividing each article in the training set into some partial articles that has the same length distributions as the development set. So, and the results prove that the results achieved on the balanced training set is slightly better than the original one. And next, I think Wenyi is going to talk about the statistical features he extracted.
Okay, so here comes the features. The first one I used was type token ratio, and it is inspired by the assignment 1 because we use type token ratio to compare different writing styles from different writers and of different writers. And I also calculated lexical entropy, and the equation is here. To identify the structure diversity in an article. And there are also noticeable errors in the fake articles. For example, the same words may appear repeatedly in a row. And I also calculate the distances between the WH words such as who, what, and the stop distances between stop words as a feature. So here are some results. So with the features mentioned above, so we can see that a balanced set performs better than the unbalanced. And I also added the number of sentences as one feature. So there are in total 9 dimensions of features. There is some improvement. Another kind of feature is the higher n-gram features. Because the fake articles was generated with trigrams, so we think the higher n-grams may help. So I built the language models of 4 gram, 5 gram, 6 gram, and 7 gram, and calculate the cross entropy on the documents. This is the result of trigram. It's not useful. I think it's because the fake article is generated with the trigram. And also, this is the previous features combined with the trigram feature, and there is some improvement. And also, we can observe that balanced set performs better. This is the in the table above, this is the accuracy used using different language models separately, and we can see that higher n-gram models perform better. In the table below, this is the result of the combination of the 4 n-gram models. It is the best. And then we combine all the features together. We can see that in the first row, the 13 dimension features performs best, and besides the third one, we will choose the first 13 dimension features as we used in the final model.
Okey-dokey. Okay. All right, so I worked on some syntactical features, namely using the Berkeley parser, which is open source. You can download it from the internet. Very simple. And so the idea was, okay, so there are certain grammatical things that are ubiquitous in grammatical sentences. You know, the presence of a noun phrase, the presence of a verb phrase, they may not appear, there might be fragments, but most of the time you're going to get good sentences, and hopefully a reasonable parser like the Berkeley parser will pick up on that. So that was the idea. And so in order to try to get useful information from this, I took like small sections of data, you know, an article size roughly, and did distributions of what each line was classified as, be that like a sentence, a question sentence, a noun phrase, etc., and created relative distributions of, all right, what fraction of them are called sentences, what fraction of them are just noun phrases. And I noticed that there were definite like thresholds that the real sets of articles would be above or below, and fake sets of articles would be above or below. And so I was able to use like give a threshold for the percentage of sentences with these grammatical features, and if it was above the threshold, then it was likely real, and if it was below, it was likely fake, and, you know, change the likelihood based on how close it is to the threshold. And then I combined these features using interpolation, just weighted according to, okay, what is really significant and what isn't. And is the next slide me or no? No, it's not. No, but so unfortunately, however, because the Berkeley parser is not particularly fast, and because we had a heck of a lot of data because of the balance set, while it turned out it was fairly effective, especially good at recognizing real articles, not so much for fake articles, and certainly not for short articles. Like one-sentence articles, completely useless, because obviously a fraction of 0 out of 1 or 1 out of 1 really isn't that informative. But in the end, we couldn't put this into the SVM simply because we kind of lacked the time and processing power. To get the Berkeley parser to run on 7,000 some articles just is not really feasible given how useful it was. But there are clearly some syntactical features that could have been useful, but in the end, we decided it just wasn't really worth putting into the final model. So.
And next I will talk about some semantic features we worked on. And I was responsible for the LDA topic modeling part. And the idea, the underlying assumption is that we think in real articles, the topics will be more focused than the fake articles. So we trained LDAs on both fake and real articles and extract 2 kinds of features, which I can pass it to Justin to save time.
Okay. So we might be late for like 30 seconds if that's okay. So for LDA, so like there are like topics here presented, and I think everyone should be familiar with it. So our last feature is another semantic feature, is long distance trigger network. The basic idea of this is like we try to model the relationship between words that is like long distance. That's why it's called long distance trigger network. So for example, if you see a word like sport, or like if you see a word sport in an article, then maybe somewhere in the article, not close to with it, but like you might see baseball because like there are some sort of like reasonable like related in the articles. So we use this, and from the distance from 5 to 15, this is another 11 features. So in the end, so we use the SVN, tune some parameters. So on the development set, we get, because we test that in the determined feature set, so in the statistical features, we get around like 86%, and like for semantic features, we get around 87%. And at the end, you have like sort of feature combinations and tune again. And so in the end, we have like around 95% accuracy for classification. And sorry for the delay, but thanks for your attention. Yeah. Okay.
Any questions?
Yeah, questions?
So, if I understood it correctly, in the beginning you said that you looked at the development set and felt that the distribution of the two things are not similar,
Yeah.
and then you tweak the training set. I don't know how good a machine learning practice is to look at the test set and tweak your training set, because you're not supposed to look at the test set, right? So I would like to...
Yeah. I think this is a really nice question. So that's why we have our development set. So like we tune on this, but this is not guaranteed to like you'll be perfect in the like testing set, because that's another set that TA will provide to do the testing. But we think this balancing is a reasonable stuff to do, so we just do it. And based on the information we have on the development set, we made this decision. But thanks. Yeah.
How do you do balancing?
So, yeah. Thanks. As you know, the number of sentences in each article is of the size 1, 2, 3, 5, 7, and so. And we just for each size we decide it's like we have a candidate pool of articles, and we first.
Do you oversample or do you generate new articles?
I'm sorry.
Do you oversample or do you generate?
No, we didn't sample. We just did it in a sequence in an order, like.
We split the long article into short one, but like if this is a long article with 100 sentences, if we split that into 10 articles, then it's like 10 short articles, but with the same tag because it's still real. Like it's a fragment of the real article.
Yeah, we keep the labels consistent.
So how is the SVM trained? Is it a video kernel or is it
We use the RBF kernel. Okay. Yes.
Can you tell us something about the speed of the classifier?
It's about several minutes, right?
For the classifier, it's pretty fast, but for the feature extraction, it takes time because, like the long distance, the long distance graph, if you want to, like the mutual information we obtain from the huge data set that TA provide, like the 1 million data sets. So, like for feature extraction, it will take in total around like 40 to 50 minutes. But like once you get the features, then we only have like 24 dimensions, which is fairly fast. So in classification, it's fast, but for feature extraction, it takes a while.
So overall, how much time does it take to classify 200 articles?
I will say around like 50 minutes. Yes.
We need to move on.
Yeah.
Questions, very good.
Thank you very much.
Thanks.
Talk a bit more about those. So with word pairs, we're looking for long-distance trigger words. And the first kind of word pairs we used were content word pairs. So we excluded stop words. And then we went through each article and found pairs of words separated by more than 3 words, 3 or more words, sorry. So they're out of the range of the trigram. And then for each of those content word pairs in each article, we got a measure of association of those 2 words in the broadcast news corpus. So those 2 words would appear many times in the broadcast news corpus, and we calculated a Q statistic for each pair. And we excluded words that showed up less than 500 times to make this viable. So we then, for each of those content word pairs in the article, averaged the Q statistics. And this gave us a measure of how often distant word pairs in the article were actually related in the broadcast news corpus. Our second set of word pair features, we wanted to find words that were related in the broadcast news corpus, but were also distant in the broadcast news corpus. For the first set of features, we didn't restrict the range, the distance between the two words in that corpus. But in the second one, the second set of features, we restricted the range when computing the association between those two words. We also wanted to know whether stop words were useful. So instead of excluding them, we just restricted it so that the word pair had to show up more than 1,000 times. Yeah. And then we found that we still had too many word pairs. So we computed the point-wise mutual information between the pair of words and just took the top 100. And if you look at the top 20 here, you can see that stop words are showing up a lot, and they seem to be capturing the fact that sentences are about particular people and particular objects. So if you have the pronoun she early on in the sentence, it's probably going to show up again later because the sentence is about a woman. And same with dollars, and same with a number like 19. So that's a sort of feature of language that this is picking up on. Our second feature was bag of words. So this is picking up in a sort of crude way on the fact that articles focus on a particular topic. And so you'll see a difference between the bag of words feature for a real article and the bag of words feature for a fake article, because the real article is going to return to the same topic words over and over again. So its bag of words is going to be sparser than the fake article bag of words. So that was a simple way of capturing the topic-centered nature of articles. Our last feature was pretty simple. It's just the variance in sentence length among the articles, because the trigram model decides to end a sentence just based on the last 3 words, regardless of how long the sentence is already. It has a lot of very short and very long sentences. So the problem that we ran into here is a lot of the development set articles only had 1 sentence, so they had 0 variance. So we got around this by adding a pseudo-sentence to each article, so that even then with a 2-sentence article, you can calculate a variance score. Then the problem was, how do we pick the length of the pseudo-sentence? We found that when we used the average sentence length, we got terrible results in those 1-sentence articles, because the mean sentence length is actually very unusual. Very few sentences are 85 words long, because the distribution of sentence length is so skewed. So we realized that the distribution was really skewed, and we decided that the true value would probably be close to the mode, that the appropriate value for the pseudo-sentence length, because that would represent a sort of a typical sentence that you would likely get if that article happened to be 1 sentence longer than it actually was. And so we tried a few values, and we found that we got very good classification results using 38, which is just a little bit higher than the mode. And so we used 3 different classifiers. The maximum entropy model models the probability that the article's real given the set of features, and then we could just use a cutoff value on that probability to classify. We also used a support vector machine and a logistic regression. We ran into a problem that we all use different programming languages, and we actually did not manage to integrate all our results. So we ended up having a different feature set for every classifier. But you can now see how these sets of features work individually. So it turns out that if you just use the word pair features, the content word pairs and the distant word pairs in the maximum entropy model, we got 84.5% accuracy. And in fact, just using content words got 83.5% classification accuracy on the development set. The support vector machine with bag of words got 61% accuracy, which is surprising. We didn't expect bag of words to do that well, actually, because the vectors are so long and so sparse. And sentence length variation alone, just one feature for each article, actually got 66% accuracy. And on the one sentence articles, with that pseudo sentence added in, it got 65% accuracy, which is just capturing the fact that some of those one sentences were really long or really short. Yeah, so that was our results. Yes.
I think that the sentence length variation is an interesting feature. Were you expecting that fake articles would have greater variation, or?
Yes, I was expecting that the fake articles would have some very short sentences and some very long sentences. So to capture that, you could have had some threshold for the number of very long or very short sentences, but just the variance seemed like a good way to capture that. Yeah.
I could not understand why, what was the problem of like combining all these approaches, because everyone was using a different programming language?
So it was inputting the features in the different formats that we'd created to one classifier. It was just right at the last minute, it turned out to be more complicated than we thought. Yeah.
So it's interesting to see that different people think similarly, because I also thought about sentence length variation. But I wonder, like, why didn't you think about using standard deviation instead of
the variance?
Other measures except for tendency that you use?
So, I mean, the variance is just the square of the standard deviation, so, yeah. Yeah.
Did you draw the distribution of lengths on the development set?
No, I didn't.
It would help you verify your hypothesis ahead of time, whether you really see a difference between them.
Yeah, just to provide some insight, I suspect that the distribution of sentence of fake articles will be approximately the exponential distribution. So that's why it's very skewed.
When I talk about the distribution of sentence lengths, I'm talking about the distribution of sentence lengths in the real articles. That's how I picked the length of the pseudo sentence to add. I didn't look at the distribution of sentence length in the fake articles at all.
One last comment. So about the classifiers, it seems to me that for binary classification, maximum entropy models and logistic regression may be equivalent.
Yeah, they may be.
Yeah.
Okay.
Thank you.
Okay, so we're talking about the same problem still, so I'll just skip over the beginning. We also use SVMs. We used SVM Lite as our package. So let's just focus mainly on the features, because that's the interesting new stuff. So we have three different types of features. We have some based on named entity recognition. We have some based on perplexity using just the word tokens. And then we also have some perplexity features where we replace the tokens with their parts of speech. So let's go ahead and look at these one at a time. So our hypothesis for named entities was that for real stories, probably the named entities that appear, for instance, the people, locations, organizations, these are going to repeat. Whereas in the fake sentences, probably it's less likely that you'll see the same entities over and over again. So what we did is we annotated each document with the named entities, just using the Stanford tools.
And we extracted four features. We have the maximum count for any overall of the named entities in the document, the same count scaled by the document length, the average count of the named entities, and then the squared sum of their occurrences. Okay, so then the second set of features is perplexity based on the word tokens. So we hypothesized that if we created larger, higher order language models, 4 grams, 5 grams, et cetera, that we would see reduced perplexity for the real documents, but increased perplexity for the fake ones. And this was motivated by the fact that we knew the fake ones came from a trigram model. And since the corpus was 100 million words, we thought that probably this was enough data that we could do these higher order language models without having too much issues of sparsity and variance. So then the features we extracted here is we have the perplexity under each of these language models, including the provided trigram. And then we also did the difference in perplexity. So originally we intended to do 4 grams and 5 grams, but we ended up cutting out the 5 gram just because the resulting language model was really large in size. So we wanted to keep our submission smaller, and preliminary results suggested that it improved the performance, but not by a lot. Okay, so then we did the same sort of idea, but we replaced all the word tokens with their part-of-speech tags. The part-of-speech tags were also extracted using the Stanford tools, the part-of-speech tagger. So here, because these language models were smaller in size, because smaller vocabulary, we went ahead and actually used the trigram, 4-gram, and the 5-gram model. So then we, in addition to the the raw perplexity and the difference in perplexity, here we also decided to try the ratio between the perplexity over the different models. Okay, so here are the results. We used the development set to tune the parameters. And so on the development set, we get 88.5%, and we get negative 0.32 on the soft metric. So for the hard metric is easy. It's just output in the results from SVM Lite. For the soft metric, we decided to approximate the posterior just using the distance between the SVM Lite results and the hyperplane. On training set, I mean, of course, we do better than on the development set. We actually get all of them right on there. So we also wanted to do some experiments just to see whether or not our performance was based solely on using SVMs or if it was, because of our choices in features. So we tried a whole bunch of different classifiers, and regardless of which classifier, we still get fairly similar performance. We do note that SVM does seem to give the best performance, but even in the worst case, we only got a 4% absolute reduction in performance on the development set. So this leads us to think that our good performance isn't just because of support vector machines, but more because of our feature selection. We also took a look at the different features to see which ones were the really useful ones. And overall, we found that the ones based on language models tended to be the most important in the classification decision. And so actually, we did an experiment where we just used those features, and we actually got very similar performance. On the training set, we missed just 2 articles, I think, 98.8%. And actually, on the development set, we did the same. So it seems like these language model features are the ones that really were essential in our project. We tried a bunch of other different features, and they didn't show much improvement in preliminary results, so we just ended up skipping them. But we did some additional things with named entities. We also tried parsing sentences, and that really didn't get us anywhere. And we tried some simple features based on properties of language. So, for instance, we looked at the count of verbs in the sentences. We also tried the the sentence lengths in documents, and that didn't really work for us. And that would be that. Just some references now. Any questions? Yeah.
So are you concerned about overfitting since you said that you have 100% accuracy on the training set?
So we actually tuned with to set the C parameter for SVMs, and I don't think we're overfitting too much here. But
when you did
Because it was.
When you say accuracy on the training set, is
Yeah.
that how do you did you train a model on the training set and then classify on the training
Yeah,
set?
we were just curious to see what happened.
Okay, so it's trained, so it's not like a cross-validation.
No. We did validation on the dev set.
With other classifiers, they are actually cross-validated, and we still end up getting like 99 points. I use a 10-point cross-validation.
Oh, okay.
Okay.
Yeah.
What was the importance of pure aspect-based models?
Out of the 5, I found out the importance of features using a random forest classifier and seeing which features were given the most importance. So both on the training set and the development set, I took the order was slightly different in both, and there were some features that ranked really low for the development set. So I just took 5 common features that came top in both, and I think out of those 3 were POSTAC based, and they were, I think, the difference between the models, POSTAC based models.
If I saw it correctly, you were using maximum count and maximum
Yes.
count divided by the document length
Mhm.
as 2 features.
Yeah.
I mean, shouldn't we just maximum count be a feature and document length be a feature, because you're using the same thing and divided by something other? I mean, intuitively, shouldn't it be just like maximum count and document length?
So document length, I thought about doing actually, but I remember seeing that the development set was just going to be truncated to certain lengths, so I didn't want to do anything there.
Yeah, but you are dividing the maximum count by the document length. So document length definitely is having some effect on your feature, right?
Yeah.
Yeah, I guess I can partly answer that question.
Yeah,
so
sure.
the classifier is SVM, and so what kernel type of kernel?
We just used linear kernel.
Yeah, so the linear kernels cannot handle the features in a nonlinear relationship like multiplication or division. So in this case, having these 2 and having the maximum, the count and the document length will not be equivalent.
So going back to the question of part of speech tags,
Mhm.
I don't know which tagger you use, but most taggers use short distance dependencies.
Sorry?
Most taggers use short distance dependencies.
Okay, yeah.
for Previous 1 or 2 words. So was that informative? Was that feature informative?
Do you want to comment on?
We didn't really look at the distance things. We just took the tagging as such. So it was based on the sentences that we got from the training set. So the models are based on the POSTACs gotten from the 100 billion corpus words.
Also, it was not tagged n-grams, just counts.
Yeah.
Question to the other 2 members. I'm intrigued by the named entity feature. So the hypothesis was that they are more common in real data.
Right.
Did you count how often they occurred in the development set in real data versus fake data?
I think that too. In the development set, yeah, in the real data again. So in development set, many of the sentences were short lengths. So this was not very effective in the sense, even in the real articles, there were just maybe one named entity which is occurring, but in the fake articles also there were one entity. There were some entities which were occurring. But as the sentence length increases, like we have one feature which is the squared sum of named entity occurrences, in which what I implemented was we considered all the entities and we checked on repeated entities. I mean, a person name is repeated or not. If the same name is repeated, then we are giving it more weight. Now that was that was getting more weights for real articles which had a significant length.
Okay, so that's more having to do with repetition, flexible repetition.
Right.
I'm more curious about the overall prevalence of named entities. The hypothesis was that it is higher in real data. I'm not sure it's true, but I'm curious if we can measure it. So the fact that the development set documents are truncated shouldn't really hurt it, because you can just count how many are per number of tokens.
Per number of documents.
Right? You can still do that. You can still look to see. I mean, my understanding is that it didn't help much. That most of the benefit came from the language.
Yeah, that was the main benefit.
I guess a quick test would be to see if it even holds in the development set. Just divide the number of named entities that were found there by the number of tokens in the whole development set, under fake and under real.
Right. that's a good idea.
Yeah, I'm betting that there is no difference because it's a very lexical thing. I mean, if you see the word Buenos, you're going to see Iris. If you see Bill, you're going to see Clinton.
Right.
With about the same, it captures it very well by the ngram, but I could be wrong. So.
Yeah, the main thing that we're thinking is more not so much how many named entities occur, but just do we see the same ones frequently?
Okay.
So that was the main motivation there.
So it's more like repetition of rare words.
Yeah.
If it's a single word or if it's a phrase.
Mm-hmm, exactly.
So I did try a variation of that. So I counted if I counted if the same named entity occurred multiple times, and I counted how many times, like if Bill occurred and if Rose occurred twice, I was counting them as 1 and 2. So there were 2 things that occurred more than 2 times. And I used that feature and I tried scaling it by the number of tokens in the document and the number of sentences, but nothing seemed to bring about much of an improvement. With that feature alone, I just managed like a 65% or a 66% on the development set. So we ended up not using it. We were not getting the right kind of normalization.
Thank you.
Mengzhu, and I'm Hao Han. And for this project, we are thinking that the important thing is we need to extract the useful features and put into the classifier. So for most of the presentation, we are talking about the work we have done for extracting the features. And the first one is a very intuitive feature that we believe if the article is generated by a trigram, then a foregram should tell the difference. And we just we formalize our idea into equations, which are not correct because that should be divided by the probability of article on the right side, but we don't care that because we want to compare the probability. And also we assume that probability of true and false are approximately 50%. So we only care that if there is a natural language or there is a trigram model, what's the probability for this article. So we train a trigram and then we use a 5-gram to simulate the real language. The result is not is good, I guess. And it is very good for the long development set, but not good enough for the short development set, which contains only one or 2 sentences. So I think from now on, we care more about the features to distinguish the sentences. And the second one is also an idea that has been talked about. It's about topic, and we use semantic similarity to measure if there is a topic, and we calculate the semantic similarity of each of these 2 words, and of course with the remove of the most frequent and least frequent words. But the result is not very good as the formal team. I guess the problem is that I only care about the semantic similarity of one sentence, and this we average the results for each sentence in an article, and for each sentence, even in natural language, there is not necessarily a topic, and for a trigram, because maybe it only has several words, and it can have a topic, so the feature is not very useful, and okay.
So we also try to use HMM to do the thing, because when HMM decodes one sentence into a POS text, it gives also the probability of this sequence. So we assume that it will give different sequence to natural language text and the trigram generated text. So we use the link pipe to do that. And the result was not very good. It's only about 61% accuracy. And the reason after analysis, we found that maybe it's because the HMM we are using is just a first order Markov chain, and it's basically similar as a bigram. So its bigram it's not able to distinguish trigram and the natural language. And so we think if we can have some kind of higher order Markov chain to train this, to make this HMM, it will give a much better result. And another thing is the noise in the natural language text, because we see many unrecognized words and many many noise, so it can harm the HMM significantly.
So we also tried some passing features. So because from observation, we found for the fake sentence, it tend to have more grammar mistakes, and at least I believe it. So we passed all the sentence, and so we try to find some features that will have different distribution after we quantify them between the fake sentence and the real sentence. So the first one is simply we normalize the sentence likelihood by the node that is the rule we used in past tree. Or the second feature, we just put the length and the likelihood together and lead the SVM to decide it. And the third feature is a little interesting. So I believe that most of the mistake made is at the leave nodes. So, which is the word to POS part. So as long as I give some proper POS tag to the word, then the pass tree can pass it, resolve it very easily. So at least I observe in the test file there's some very wrong POS tag that is given from the PCFG parser. And so the way I quantify it is try to see how surprised I see this POS tag given to give it to certain word, and I found the one with most higher surprise within each one sentence, and is this one feature. And the next one is so I believe that the rules that used for the fake sentence and the real sentence will be different. At least the distribution will be different. So I try to capture that, but I think it will not be the best way. So I've calculated the standard deviation and the mean of the rules probability for the rules used in the sentence. Yeah. And the last one is I want to find some topological pattern in the past tree. The way I do it, this is a very naive one. I just try to see how complex this past tree is by use the number of rules and divide by the length of the sentence. And the result is very disappointing, and it's all around 50%. And I guess the reason is just because my assumption is wrong. I mean, I looked into the detail of their distribution. Actually, they have so many overlaps between fake and the real sentence. And also for the PCH parser, it seems like it's not very good parser for the broadcast data. So it's maybe another part of the reason.
Okay, so another approach we tried is try to use different models to analyze the same sentence and see if they give the same answer. So there are two kind of POS taggers available online. One is MaxN tagger provided by Stanford NLP, and another is HMM tagger provided by LingPipe. And so the idea is if we have one natural language sentence, then we use both of them tag, assume they work very well, then they tend to give the similar sentence, similar tags. But if there's some fake sentence here, and we use both of them to tag it, then they will make mistakes, and the mistake will vary a lot. And so we calculate this by just counting the number of difference divided by the length of the sentence. And however, the result is again not very good. It's even less than 60%. And so we think the problem here is that first of all, the noise in the natural language sentence is too hurts both of the models too much. So even for some sentences, they don't give they give totally different tags. And another thing is that because this approach is only it only aims to analyze short sentences, and for short sentences, this fake data is too real. I can just say it's too real. It's not able to distinguish them based on the tags it gets. Okay, another approach we try to deal with short sentence is to use the linguistic rules. And the idea is we want to have one sentence and tag it. We have POS tags and see if there's some grammar mistakes looking at the text. For example, if you have two conjunction words together, then it must be wrong. But we didn't go into detail on this because one thing, there's too much noise in the natural language text. Another thing is that our ngram model is too good. So given the time limits, so we didn't investigate much on it.
And I also tried the specific phrase. This is similar like the Bagels words, and I used the light side to extract the features, and the features are contained bigram, trigram, and the bigram POS. So I extract more than 1,000 features from the training set, and the test result on the training set is about 75%. And but this must be not usable in the development set because the development set some Bagels words are different, and because I generated Bagels words based on the training set, so they are biased. And so too specific, just focus on the training set. So when applied in the development set, some phrases is not useful. So this idea, I think, is just maybe more focused on the topic classification. And I also tried the general statistic analysis. The features contain the mean of the word's length and the standard deviation of the word's length, and the mean and the standard deviation of the sentence length, and also the vocabulary diversity, such as the score of the ratio of the type token, and some scores. I used the two scores. One score is calculate the diversity, calculate the times according to the words which happened only once, and another score is to calculate the scores which happened more than once. So these two different scores, and use all these features. This feature generates 7 features from the general statistic, and the test result is about 97 on the training data, but not so good on the testing data, because in my opinion, that because the model is overfitting on the training data. For example, because in the development set, some articles they all contain the unigram words. They all contains the words which happen only once. So when I apply the scores on the development set, all these scores becomes useless to classify the real data and the fake, and the real article and the fake article.
Okay, so we will be wrapping up very soon. So the classifier we are using is SVM, and there are a bunch of things we need to do in the future. Maybe we need to choose see all kinds of classifiers, and maybe put all the features together and find the best features. And that's all. Thank you. Yes, yes.
So when you analyze the errors, you refer to the noise in natural language several times. So what is exactly this noise?
This noise is kind of like we guess this is from what is a broadcast, and you use some machine to translate it into text, right?
You mean speech recognition?
Yeah, speech recognition, right? So it seems that some of in the sentence we always see some very fragment, broken sentences in the natural language, and some words were not recognized, and some given unknown tokens and all sorts of stuff, and yeah, that kind of noise. Yeah.
So I don't think these are a result of speech recognition.
Okay.
They are a result of manual transcription.
Oh. Okay.
Unless I'm completely wrong, but I think that's what the broadcast news is. But there may be error in transcription, and I think mostly because it is spontaneous speech.
Okay.
It could be that people said something and they stopped in the middle and said something else. There are disfluencies.
Yes. So that's a problem. Yeah. Yes.
So what was the accuracy on the dev data?
On the dev data, it's 92%. Yes.
So in the presentation, though, it said that it was like 72%.
No, that was another yeah, different features. So finally we just use that n-gram model, and we put the value of 5 gram and 3 gram together, and so only two features.
Just one
Yes.
comment to also what I saw before. You can spend a lot of time building different classifiers with different feature sets, and in the end you find out whether it worked or not. Many times it doesn't work, as you found out. Sometimes it's faster to just test this hypothesis on a labeled development set to see if really there are differences there.
Yeah.
Okay, thank you.
Okay, thanks.
So, same task as before. Everyone knows what we're talking about. So I just jump right into the features to start. We have like 2 classes of features. One is our more linguistics features, and we have another set of topic model features that we used. We originally designed our features based on the idea that we would tag and parse the data using TurboParser from Noah's group. It's a dependency parser that also produces tags. It's fairly accurate. We used it in order to get dependency relations. And our first feature here is just the document length in words. Our second feature is the number of DEP relations. And DEP is just the arbitrary label for the dependency relation that couldn't really figure out what the relation should be. So we assumed this would be more common in the fake articles where there would be a bad parse and there would be a lot more of these unknown labels. And the second feature here is the number of bad consecutive tags, which we were considering to be 2 determiners in a row, 2 conjunctions in a row, and 2 POS, which is the apostrophe S in a row. And this wasn't actually that useful. We thought it would be more useful than it actually was because this didn't even occur very often in the fake data. And this was normalized by the document length. And the last one here is the number of repeated words in each document, just the number of tokens themselves that were repeated throughout the document. And this was also normalized by the document length. And we used these along with some topic model features that Mario will talk about.
Yeah, so we just used LDA and created 20 topics using 30-line segments from the 100 million word corpus and treating those as documents. And that seemed okay because most of the news segments were much longer than 30 lines, so you weren't that likely to be overlapping across 2 segments on different topics. And then we ran inference on the train and dev sets, and we did some variants. So we took the median topic probability and the standard deviation of the topic probability and the maximum topic, and I guess those are all just trying to get at how uniform is the topic probability, because if it's on a specific topic or more focused, it should have a less uniform distribution. And on various algorithms, you can get generally in the high 90s across most different algorithms using these on the train set. But because the performance is much worse on short documents, the performance on the dev set was not nearly that high. Then I guess we can just go to the next one here. So we used the Weka toolkit to do these, and the accuracies using the different features were that the part of speech and repeated words features were not very helpful on their own. The LDA topic features could get 76%, and when you combine them, you got 85% accuracy.
Our classifier was logistic regression and SMO, right? We tried both?
We tried a few ones. They logistic regression and SMO got similar results. They were both in the mid 80s.
Right.
So
this is some more general issues and what we had encountered and tried to do. We wanted to include more language model features like the foreground language model that we had made. We didn't end up having to be able to use it because we ran out of time. We thought that might be useful, and we also wanted to refine our list of linguistic features, which some of them were less helpful than others. The repeated words feature turned out to be actually somewhat useful, right? That one and the median topic model probability.
The dep rate was also.
The dep rate was also useful just because
the bad combination of bigram POS tags.
That was less useful, right?
Not very useful.
So that one was one of our intuitive things that was, empirically not as useful as we would have assumed it would be. And those are the general issues we tend to encounter. So, any questions? Yes?
Can you present the accuracy that you train the training set, then actually on a development set, right?
That's correct.
Yeah.
Okay.
But with the training set, it would be.
It would be almost 99.99. Yeah. Mm-hmm.
So when you said the median topic probability, so it's a median across what?
Across the 20 topics.
Okay.
Yeah. That turned out to be the most helpful, and it was like if you saw the distribution, as the document gets longer, it approaches a value, like the range of medians gets very small for the fake documents.
So why don't you take the max?
Because if the shorter the document is, the more likely it is to have a high max, because there's just less opportunity for some other feature, some other topic to get probability, because there may be like something like affirmative action will appear, and then it will get high probability for one topic. And if there's not another strongly associated word, then it won't get high probability on other topics.
High variance.
Yeah, basically high variance.
The values of the median topic probabilities will be quite small, right? Because the median will be
Yeah, they'll all be small, but they should be higher for the fake documents.
Okay.
Did you try with a different number of topics and see if that changed anything?
No, because running the LDA topic model takes a long time. So we could have, it seemed like maybe it would have been better to try with more. So we didn't actually tried running it on the full 100 million word corpus, but it actually ran out of memory. So then we did it on just like a portion of it. And if probably it would have been better to do more topics on a larger amount of data, but it still was very good at distinguishing the training data. I think the high variance would have still been a large issue on the development set, though.
You mentioned that you tried both logistic regression and SMO.
Yeah.
SMO SVMs.
I'm sorry?
SMO is a kind of SVM.
Okay, it's a package name?
Yeah.
It's
in
the
Weka.
name of an algorithm of training the SVM.
Okay.
And we use quadratic SVM kernel. for
Okay.
that.
So
Actually,
what is
linear
about
worked best when we
SMO?
added in the other features. When it was just the topic features, quadratic worked better, but linear worked better when you added in the repeated words feature. I guess we could have included some graphs, like if you graph the repeated words feature against the median topic feature, you can draw a straight line that gets all but like one or two of the instances in the training data. So it's pretty clear separation, but the variance gets too high on the short documents.
Yeah, those short documents are-
Yeah.
All right, thank you. That's wonderful. I was worried about that. So I hope that you found it useful. I appreciate that you didn't repeat all the things people before you said, so we'll do the same thing on Wednesday. In some sense, people who come later have an advantage, a disadvantage, depending on how you want to look at it. You don't have to repeat things that other people said. You don't have to say things for the purpose of saying them, just communicate very informally, and I think most of you've done that, so that's good. Since we have a few minutes, I want to pitch a few things. One, the FCEs are open. I encourage you all to go and register your sentiment, be positive, negative, or otherwise. These FCEs are important, they're useful feedback. Specifically, this course is taught a little bit different, I think, than most courses in the sense that it's very talking and hand-waving and stuff. So I'm very curious to know if this is successful or not successful, if you like it, if you'd rather have the more traditional way of teaching, then please be honest. I do read all the feedback. It is anonymous, but I absolutely read all the individual comments as well as the statistics. So please don't hesitate, please don't forget to do the FCs. You're probably going to get reminders by email, or at least the undergrads get reminders by email. I don't know about the grad students. But go after the system and fill it out. Beyond the FCEs, if you want to come by and talk and just give me your feedback, ask questions, please do. This is actually the part of teaching that I enjoy the most. You can come in after the lecture or separately and shooting the breeze. So don't be shy about it. Any other comments, questions? Yes.
So I already spoke to the TA. I have a conflict tomorrow at Wednesday at 2 o'clock.
Okay.
And we are like starting at the end.
Right.
So if anyone wants to just like.
Right. If we had known about it before we scheduled it, we would have made sure to put in that constraint into the randomization. Since we didn't know, you need to look for volunteers. So you're looking to swap with someone who is scheduled in
First or the second one.
first or second. So who are the first and second team? If either one of you is willing to go to, is this the end, the last one, or
Yeah.
you would have
So it's on the same day.
our gratitude. Think about it, talk about it, let us know.
We are the second team in also school. We don't care, I don't know. We don't care about the word.
So for the questions, so because on the clusters, I think like a lot of groups just delete some of their like models because the upload space is limited, and like we work on that. I think like we have that issue like yesterday or something. So at the point when TA wish to run up like each team's pipeline, so what should be the way we put back our model and make it
Well,
stuff?
what I suggested is that I suggested to TAs that they just copy over one model at a time, that you keep your big files on your private space.
Yeah.
If they can run it from that space, fine. If not, they could copy it over. I apologize for that. My mental model of your disk needs is not kept up with reality. I did get the partition doubled from 5 gig to 10 gig, but it came too late. It came this morning. So I apologize for that. I'm amazed at how much space people can take, but I think it's a general rule that you take the space that is given to you. Yeah, there's no constraint on taking space.
Yeah, none of us realized that we were sharing a space until yesterday.
Right. So yeah, just leave the files wherever they are, and just provide pointers. Hopefully you've provided the pointers. If not, provide them now to where the files are. Don't touch them, so freeze them. We call it self-freeze. Freeze them yourself. Make sure to not touch them after the deadline. But other than that, be fine. All right, we'll see you one more time.